Okay, good evening. This is Professor David J. De Los Reyes. Okay, my topic for tonight will be an interesting one. The topic is actually regarding projectiles, that is an application of second order differential equation. Okay, let's proceed. My lesson for tonight is DE 47. Subject matter second order differential equation. It is under the application, and that application is regarding projectiles. This is a battle of the tanks. What will be the importance of differential equation in the battle of the tanks? Actually, I think they use the software regarding differential equation in the what they call this determination of the total distance that could be traveled by a projectile. Okay, let's proceed. I will try to explain the figure. We are given a problem here, so this should be a horizontal line, and this should be a projectile here. It could be an M1A1 Abrams, maybe a battle tank of the United States of America. The projectile of this, the nozzle of this projectile is at a certain angle theta with respect to the horizontal with the given initial velocity. Okay, I will try to give you the, what they call this, data for this problem here. The initial velocity of the nozzle of the given problem is, what they call this, 2,000 feet per second. Okay, and angle theta, the angle of firing is 5 degrees. The condition, the problem is Ry is approximately 0, and By is also approximately equal to 0. Meaning the effect of the resistance along the y-axis is almost 0. It's not 0, but it's very negligible. And the velocity with respect to the y-axis is almost 0. With the given initial velocity of 2,000 feet per second and the angle of firing is 5 degrees, the problem is asking for what will be x as a function of time. What is x? X is actually the total distance traveled by the projectile along the horizontal. So if we fire a projectile here, the path of the projectile is something like this. They say it's a parabolic curve. Okay, this should be the maximum height attained by that projectile, and the total distance traveled by the projectile with respect to the origin is actually this distance here. This is designated by letter R under the topics of projectiles. R is the maximum range. I think the significance of this problem here is that if we fire the projectile here, what will be the total distance that it could travel? I mean, if this is the enemy, what will be the, what you call this, the distance of that enemy with respect to the origin or the projectile for it to be hit? Okay, so the problem is asking for what will be x as a function of time. And what will be the significance of this? Because as soon as you fire the projectile, at any moment in time, we could compute for x. And if the distance of that enemy from the origin is actually maybe 12 miles, if we fire it at an initial velocity of 2,000 feet per second, could we hit it? Okay, that's the significance of this x as a function of time. Okay, let's proceed. I bring out a free body diagram here. This circle here represents the, what you call the shell of the projectile, of the cannon, maybe the M1A1 Abrams. Okay, this should be the y-axis, this is the x-axis. If the projectile is fired, okay, according to the given condition of the problem, I didn't read the problem, but I am now explaining it. Ry over here is at almost zero. So if the resistance along the y-axis is almost zero, the only force acting on the shell will be Rx. And for the given problem, it was given that the resistance of air to the shell is actually 100 over 25G times dx/dt. It is given as this. The resistance to motion of the shell acting horizontally against it. Okay? So this is actually, so if the motion of the shell is something like this, Rx should be opposite that motion. Okay? And it is represented by the equation. It was given by the problem. 100 over 25G times dx/dt. So if we now try to bring out or find the relation of x as a function of time, x is actually the distance traveled by the projectile at any moment in time. We are interested in that one. Because if we know that the enemy is within a range of 8 miles, and if we fire the projectile at a speed of 2,000 feet per second, could we hit it? That's the problem there. Okay, let's try to bring out the solution of this. The solution of this is actually by using differential equation. So maybe the software, okay, they use in that so-called M1A1 Abrams to calculate that horizontal distance at any moment in time come from the differential equation. Okay, let's try to bring out the solution. Summation of forces along x, okay, and this should be equal to, this is actually, force is equal to MA. Why I take the summation? I put the summation here, the notation delta, because there could be many forces acting on the shell as it flies. But the problem is, it only indicated that the other resistance to motion is negligible. And the only one acting on the resistance to motion is Rx. And that is 100 over 25G times dx/dt. So if we now try to take the summation of forces acting on the shell, it's only one. This is only Rx. Okay? But what will be the sign of Rx? Rx is against the motion, right? The motion is to the right. If the motion is to the right and Rx is against, the sign of this Rx should be negative. Okay? And there are no more forces acting on the shell, because the other ones are very negligible for this given problem. So it's only Rx. So the left hand side will be only the negative Rx equal to 100 over G times d square x over dt square. Because mass is actually weight all over gravitational acceleration. The given weight of the shell, I forgot that one. The weight of the shell is 100 pounds. Okay, so this is 100 over G. Under the English system, this should be 32.2 times d square x over dt square, because the second derivative of x with respect to time along x is actually acceleration along x. So this is 100 over g, that is actually m, and ex is actually d square x over dt square. At any moment in time, as the projectile flies, this x here is variable, so the second derivative of x with respect to time is the acceleration along x. Okay? So, but what is negative Rx? Negative Rx is actually represented by this. Rx is given as 100 over 25G times dx/dt. So what happens to the left hand side now? I will check the camera. What happens now on the left hand side, as we put the value of Rx, this should now be equal to negative 100 over 25G times dx/dt equal to 100 over G times d square x over dt square. 100 and 100 cancel out, right? They will cancel out. This G here cancel out also, right? So what happens now? the coefficient of the right hand side now will be unity, right? I rearrange it, so d square x over dt square, and this one is negative. I put it on the right, okay, then I rearrange it. So meaning this negative sign, it will be transposed to the right hand side, so it will now be plus. And 1 over 25 is 0.04 times dx dt equal to 0. The variables here are x and time. Okay? So we are now given the second derivative of x with respect to time, and the resulting equation is termed to as second order differential equation. Because to compute for x as a function of time, we must have to solve the solution of this one. And the solution of this one, there are three possible cases, right? Real and unequal, okay, equal and real, and the third one is the complex thing, right? So how do we know if it's case 1, case 2, or case 3? Let's bring out the solution of this one. We let x to equal to be k e to the mt, dx dt will be equal to km e to the mt, second derivative will be km square e to the mt. We will get the value of, we do not have x on the second order differential equation, right? So what only we need is only dx dt and the second derivative. So if this is now the second derivative, we're following this. Plus 0.04 times dx dt. Dx dt is actually, I forgot this one. This should be km. This should be with an m. Right? Dx dt is km e to the mt. And this should be equal to 0. There is a common factor k. We could remove it. Right? E to the mt is common factor, right? We could remove it. So what remains? M square, 0.04 times m is actually 0.04 m, and this should be equal to 0. So this is now our characteristic equation. We are given a quadratic equation. The quadratic equation is actually m square plus 0.04 m, and this should be equal to 0. So to solve the solution of this equation here, we'll try to solve for the possible factors of m. And luckily, this is an easy money, right? We factor out m, right? We bring it out. So what remains inside will be m plus 0.04 close quantity, and this should be equal to 0. This is actually m. Right? Or if you want to place the property, you could have minus 0 over here. It doesn't change the value, right? So the possible factors of this, you don't even have to, use the quadratic equation. It is now factorable by inspection. M minus 0 quantity times the product of m plus 0 for close quantity, and this should be equal to 0. To solve for the possible rows, this is now algebra. Equate its factors to 0. M minus 0 equal to 0, therefore m1 now will be equal to 0. Right? The first value of m is 0. If we transpose this to the right, there is no such thing as plus 0. Right? So when 0 is positive or negative, it is still 0. Right? So m1 will be 0. We take the second root, m plus 0.04 equal to 0, therefore m2 now will be equal to negative 0.04. Okay? 0 is a real number, negative 0.04 is a real number. They are not equal, okay? So real and unequal, so this should fall under case number 1. So the resulting solution now will be x, yx. This is d square x over dt square. The variable is actually should be x. X should be equal to k1 a raised to m1t plus k2 a raised to m2t. Okay? But m1 is 0, right? So 0 times time will be 0, and e to the 0 will be 1. So k1 times 1. The multiplier is just 1, or just simply k1. The second part, since we have a value for the value of n2, this should now be k2 plus e raised to n2t. This is negative 0.04 times time. This is now our general solution. We are now given the relation of x as a function of time, but for the meantime, we do not know the value of k1 and k2, so this is still a general solution. Okay, let's try to compute for the value of k1 or k2. Initially, at time t equal to 0, x is equal to 0. How is that? It's easy, guys. At time t equal to 0, we didn't fire the projectile yet, right? At time t equal to 0, the distance traveled by the shell is 0 because we haven't fired it, right? Initially, at time t equal to 0, x will be 0. This distance here will be 0 at the time we didn't fire it, right? So at time t equal to 0, I place it in x is equal to 0. 0 should be equal to k1 plus k2. At time t equal to 0, negative 0.04 times 0 will be 0, and e to the 0 will be 1, so this is times 1. What happens now? 0 will be k1 plus k2, or k1 is equal to negative k2. Okay? That's the relation of k1 and k2. We could call this one equation number 1. We now produce a linear equation involving k1 and k2. So to compute for the value of k1 and k2, let's try to bring out another relation of k1 and k2. And to bring out the relation, we will take the derivative of x. The derivative of x with respect to time will be dx dt equal to the derivative of k1 will be 0. The derivative of the second one will be k2 times the derivative of the exponent. The derivative of the exponent is negative 0.04 times 1, or negative 0.04 times k2. This should now be negative 0.04 k2 e raised to negative 0.04 t. Okay? We are now given the first derivative of x with respect to time. Okay? Again, let's try to compute for the value of k2. At time t equal to 0, dx dt will be equal to, what is dx dt? It is speed, right? It is speed. Okay, I will try to erase this one, so you will understand. It is something like this. This is the horizontal ground. This is the nozzle of the M1A1 Abraham. The initial velocity is actually 2,000 feet per second. This is the origin, initially. For this initial velocity, this is with a certain angle theta, right? If this is projected at a certain angle theta, and this is actually 5 degrees, this total velocity should have an initial, meaning should have a component along the x-axis, and that is represented by x. And it should have also a vertical component. It is represented by by, okay? So if we now try to compute for vx, okay, vx will be, it seems we are given a right triangle, right? This is bx, this is by, and the hypotenuse is bo, and this is angle theta. So bx obviously is actually the hypotenuse times the cosine of this. It is bo cosine of theta. And this bx here is actually dx dt. Right? So at time t equal to 0, dx dt will be equal to bx, and that is actually equal to the initial speed times the cosine of the angle of firing. So I place it here. At time t equal to 0, dx dt is actually bx, and that bx is actually the initial speed times the cosine of the angle of firing, right? We are given the initial speed, 2,000 feet per second, cosine of 5 degrees. Cosine of 5 degrees is almost 1. So if we try to multiply 2000 by the cosine of 5 degrees, what will come out will be the velocity along x is very powerful. It is 1992.88 feet per second. So the problem is actually correct because with that certain angle theta 5 degrees, if we try to compute for Vy, this Vy here is very negligible, right? If the angle of firing is small. So the what is needed actually here is actually Vx. That's the one firing the shell to the enemy, right? So if we now know that at time t equal to 0, dx dt will be 1992.88 per second, we will use this equation here. 1992.88, this should be equal to negative 0.04 per parenthesis times k2. At time t equals to 0, this will be 1, right? So this is times 1. And we can now compute for k2. K2 will be 1992.88 over negative 0.04. This is a very small number. 1992.88 divided by a small number, it should be a negative, big number, but this is negative sign. Okay? So if we now know the value of K2 to be negative 49,810, the value of K1 by using equation number 1 is actually negative open quantity. The value of K2. Negative, negative, this will now be plus. So K1 is actually 49,810. So the resulting equation now will be x equal to, I will place it here for you to see, right, guys? We'll go back here. X now will be equal to K1. K1 is 49,810 plus K2. What is K2? Positive. Is it plus? Oh, minus. K1 is plus. K2 is minus. Minus 49,810 times e raised to negative 0.04 times time. So if we try to simplify this one, common factor, 49,810 times the quantity 1 minus e raised to negative 0.04 t. So this is actually our final answer. What will be the significance of this? We could compute for x if you specify time at any moment as you fire the M1A1 Abrams, right? Okay. If you place this one to be 12 miles, what will be the elapsed time? For how long will the enemy be shot if this is 12 miles? For how long? We could solve for it because we are now given the relation. Okay. So that's the significance of this. 49,810 is actually in terms of miles. 49,810. 1 mile is 5,280 feet divided by 5,280 feet. This is approximately 9.43 miles. So actually the problem projectile here got a range of 9.43 miles. It could hit any enemy within a range of 9.43 miles. So if the enemy is within 5 miles, okay, within 5 miles, of course you will not fire the projectile at 5 degrees. It should be a higher degree, so it will go shorter, right? At 5 degrees, it is something like this. At maybe 30 degrees, it is like this. Maybe at 45 degrees, maybe it is like this, right? So it depends. So this will be the significance of differential equation in the Battle of the Tanks. And in the Battle of the Tanks, that is termed to as projectiles. Okay guys, if you like my lecture, please click like. If you want to subscribe to my channel, please click subscribe. My channel is at youtube.com/@ProfDavidJ.De And if you want to share it, please click share. Good evening, Los Angeles.